In this video, we are going to present two illustrations of the application of a square contingency table. A square contingency table is commonly used for error assessment in the remote sensing and GIS fields for measuring the difference between two maps. One of the techniques suggested for comparing pairs of maps is the use of two parameters called quantity difference and location difference. This technique is described in a paper published in the International Journal of Remote Sensing. Quantity difference is defined as the amount of difference between a map at time t and a map at time t plus 1 that is due to the less than maximum match in the proportions of the categories. We see an example of a square contingency table on the right, which shows the cross tabulation between the number of elements for each category in the time t map and the time t plus 1 map. Quantity difference for a given category can be found looking at the total column and the total row for that category. If there is any difference between the two values for a given category, then it corresponds to quantity difference. Allocation difference is defined as the amount of difference between the map at time t and the map at time t plus 1 that is due to the less than maximum match in the spatial allocation of the categories, given the proportions of the categories in the time t map and the time t plus 1 map. The sources of allocation difference can be separated into two components called exchange and shift. We can see in these figures a graphic representation of the types of difference between the map at time t and the map at time t plus 1. In this example, we have three categories, A, B, and C. First, let's notice that in these examples, there is no quantity difference. For each category, the values in the total row and total column are identical. But the allocation of the categories is less than maximum. Exchange occurs when, for example, one element classified as A at t plus 1 is classified as B at t, and an element classified as B at t plus 1 is classified as A at t. From this definition, we establish that exchange involves at least two categories. Shift refers to the difference remaining after subtracting quantity difference and exchange from the total difference. The quantities are identical, but the allocation of the categories is less than maximum, but exchange is not occurring. Shift occurs when, for example, one element classified as A at time t plus 1 is classified as B at time t, but the opposite case does not occur. That means there are no elements classified as B at time t plus 1 that are classified as A at t. One of the implications of this definition is that for shift to occur, it is necessary that one of the maps has at least three categories. We evaluated these concepts in two applications, change analysis and error assessment. In the first case, we applied the concepts of exchange and shift to the analysis of land cover change through time in the Plum Island ecosystems LTER study site, using the land cover maps produced by the Office of Geographic Information of Massachusetts at 30 meters spatial resolution for 1971, 1985, 1991, and 1999. We analyzed the changes in three land cover categories, forest, build, and other, in three time intervals. The y-axis of this graph shows the amount of change divided by the number of years of each interval. We found that in all three intervals, quantity difference was the largest type of difference. In the first interval, exchange was almost zero, and shift corresponded to the largest proportion of allocation difference. In the second interval, allocation difference increased, with exchange being the largest amount of allocation difference. In this second interval, shift was almost zero. In the third interval, both exchange and shift increased. Also, we found that at the category level, in the second and third time interval, the largest exchange occurred between the categories of forest and other. The figures at the top show that forest and build are mainly responsible for the quantity difference. Forest and other are net losing categories, while build is a net gaining category. We also apply the concepts of exchange and shift to evaluate the accuracy of the classification of fine spatial resolution aerial imagery into 7 land cover categories for each of the 26 towns that are part of the Plum Island ecosystem study site. For this application, the calculations are the same. In this case, the map at time t corresponds to the comparison map, and the map at time t plus 1 corresponds to the reference map. In this graph, we can see the sources of difference separated into the distinct components: quantity difference and location difference represented as exchange and shift for 3 of the 26 towns of Pi. We found that towns with similar overall difference may show distinct sources of difference. For example, Woburn and Newburyport have nearly equal overall difference. Newburyport has less quantity difference and less exchange than Woburn. Woburn has more exchange difference than Newburyport. On the other hand, Ipswich and Newburyport have nearly the same quantity difference. Ipswich has more exchange and more overall difference than Newburyport, while Newburyport has more shift difference than Ipswich. At the category level, in Ipswich there are several categories contributing to exchange, with the largest exchange occurring between deciduous forest and coniferous forest. In Newburyport, the 2 largest exchanges occur between fine grain and bare soil, and between fine grain and deciduous forest. Here we can see the 3 components of error for each category in Ipswich. The comparison map shows more fine grain and wetlands than the reference map shows, while the comparison map shows less of all other categories than the reference map shows. The label C less than R means that the area of the category in the comparison map is less than the area of the category in the reference map. The label C greater than R means that the area of the category in the comparison map is greater than the area of the category in the reference map. Now I'm going to show you how we can calculate these measures of difference. Professor Gil Ponius has developed an Excel program called Ponius Matrix. First, the user is going to find the documentation tab, which includes the description of the content of the file, along with the instructions for its use and reference to the main papers that describe the methods implemented in this program. In the sample count tab, the user must enter the contingency table resulting from the cross-tabulation of the reference map and the comparison map. The user can choose between conducting an error assessment or a change assessment, which basically changes the labels in the resulting tables and graphs. If the data come from sampling, the user will have to choose the sample option in this cell, and then fill in column A with the population totals. This will correct the sample count to population count, assuming it's a stratified random sampling. If the user has all the information from the population, then the census option must be chosen in this cell. And then it is not necessary to fill in this column, as the calculations will ignore it. The Figures Data tab shows the calculated metrics for quantity difference and for allocation difference, characterized into these 2 components, exchange and shift. In the exchange tab, the user is going to find the calculated exchange values between the different pairs of categories. Finally, the Overall Components tab shows a figure with each of the components of quantity and allocation difference. This work has been led by Professor Gil Ponius and assisted by Ali Santa Cruz. We recommend the users to read the paper published in the International Journal of Remote Sensing, which presents the techniques shown in this video. The link is provided in the description section of this video. Any additional questions can be sent to Professor Ponius' email address. The Excel program as well as a program developed in the R language are available for free download from the website listed here. We'd like to thank the National Science Foundation for their support through the long-term ecological research program in the Bloom Island ecosystems. Thanks.